So thank you, Dr. Santiago. With your permission, I will stand because I'm more comfortable standing. So thank you too to the Campus de Mar for the opportunity to come and speak to you. It's given me an opportunity to stay in one of the most beautiful places I've ever been in, Bayona, and I'm very grateful for that. What I propose to do today is to talk to you about a topic that spans economics, ecology, hydrology, at minimum, plus some other disciplines. So this is going to be further from the center of economics than most of the talks that will have appeared in this series before. It's a topic which also spans the oceans and the land. So it is very much in the middle of a number of disciplines and in the middle of a number of biomes. The work I'm going to talk about is collaborative with Silvio Simonit. Silvio is a postdoctoral fellow on a research program of which this is a part. And he was responsible for much of the heavy lifting work that was involved in generating our results. I'm going to give you the abstract, and that's in a nutshell everything I'm going to talk about. So you can read that, and then if you leave, you will have missed nothing. Essentially, our problem is the following. If you buy a piece of land, what you are buying is a piece of an ecological system, an ecosystem. That land has certain properties. They may be properties that lie under the soil, minerals and so on, gases. They may be properties that include the vegetation on top of the soil. And it is the combination of these properties that give the land value. Its location, its productivity, its relevance to the production of things that you are interested in. Every piece of land is capable of multiple products. So every piece of land, if you have to model the production function, is a joint production function. And essentially what we're doing is saying, what are the joint production functions of land in a particular part of the world that impacts the oceans? And the part of the world we've chosen is the Panama Canal. The Panama Canal, as everyone here will know, is responsible for something like 5% of global maritime traffic. It has many, many advantages to shippers, including a reduction in the cost of shipment, but it has advantages to the rest of the world in terms of a reduction, for example, of carbon emissions associated with the movement of ships, because of the fact that it cuts off a very large part of the traffic that would ordinarily have gone around the bottom of the continent of South America. Right now, the Panama Canal is in the middle of a very significant expansion program. That expansion program involves the development of new locks. So this is what is known as a Panamax ship. It's a vessel of the maximum size that can be contained by the locks that currently exist in the Panama Canal. Under the expansion, these ships will be significantly enlarged. So this is a Panamax ship. The expansion of the canal introduces what are called post-Panamax ships. These are currently being built around the world now, and they will be significantly larger in volume. So when the canal is expanded through the introduction of the post-Panamax locks, it will be able to take a greater share of global maritime traffic. And there are many, many potential advantages that spring from that. Now, what makes this interesting to people like myself and Silvio Simonit is that these locks are served by a watershed that supplies them with water. So every lockage takes approximately 200,000 cubic meters of fresh water. Every time a ship comes into a lock and passes through, there is something like 200,000 cubic meters of fresh water that is then passed out to the sea. So that water derives from the watershed of the Panama Canal. It's an area of something like 3,000 square kilometers in a landscape where there is highly variable rainfall. But essentially, those locks are supported by the vegetation, the land use in the watershed of the Panama Canal. So we're interested in the efficiency of a program to make sure that the post-Panamax locks will work by looking at the impact of changes in vegetation around the watershed. This is the area. It is the Panama Canal, as I guess everyone will also know, paradoxically, goes from the Caribbean to the east to the Pacific to the west. Because at this point, the state of Panama is in the shape of an S, and the passage from the Caribbean to the Caribbean to the Pacific goes in the direction from the north west to the southeast. From now on, this gray area represents the coastline. From now on, all you will see is maps of the canal watershed, because that's what we're going to focus on. And this first map here just shows you what the canal route looks like. It passes through the Lake of Gatun, which is what feeds the locks. That lake is in turn fed by the watershed that includes all of these river systems. There is some old growth forest in the extreme eastern part of the watershed. Most of it is currently in grassland. So this has been cleared to make it possible to raise cattle and so on. The functioning of the canal is not an issue in the wet season. There is plenty of water to fill the locks. The functioning of the canal is only at risk during the dry season. So we're looking at a problem which exists because of variation in rainfall. Dry season flows are needed to maintain the ability of the canal to operate. And if we look at what happens to the rainfall, there are several different things that occur to it. Most is lost to evapotranspiration. This is a term which refers to the loss of water that occurs from trees, from leaves. So what trees do is pump water out of the ground, and then they release that water to the atmosphere. They pump water out of the ground through the roots. They process it to generate the foods that make the tree growth possible, and then they release that water. So most water that comes down is lost to evapotranspiration. 1/3, a little bit less than 1/3, is used currently for the operation of the locks. 13% is used for hydroelectric generation at a power plant, and that's a power plant that is at this location here that I'm now illustrating. And then some other is used for fresh water supply, and some is spilled out of the lake during the wet season. So the expansion of the canal is going to increase the requirements of this share here. It's going to ask the watershed to yield more water in order to be able to operate the locks. Now, our analysis is one that is going to, first of all, I'll give you a little bit of background of what the vegetation, the rainfall, and so on of this region looked like. I will then give you some insight into the economic problem, and then I'm going to report the results of the modeling work that we've done on this issue. So to begin with, this is the wet season rainfall here on the left-hand side of this panel, and this is not the period that we are worried about. In the wet season, there's plenty of rain. It's used to store water in this lake here, the Madan Lake, and it's used in storage of water in the Gatun Lake. In the dry season, rainfall is both very variable, but for most of the watershed is quite sparse. There's not much rain. So the worry is what happens during that dry season. Now, the Panama Canal Authority is currently reforesting the watershed with a view to increasing the reliability of water supply. So their aim is to cover the whole of the watershed with forests as it was originally, and what they think they are going to get out of that is a more reliable source of water in the dry season. And they think that this will make it possible for the post-Panamax locks to work in the dry season. So that's the belief that the Panama Canal Authority has. So they've looked at the clearance of the forest as a problem. And worldwide deforestation is thought to be a problem for various reasons. It affects a number of the benefits that we get from our environment. Those benefits we typically refer to as ecosystem services. And I know that that's going to be a concept that will be strange to most people, but I'll give you some instances of this as we go along. But the production of food is an ecosystem service. The production of a fishery, for example, is an ecosystem service. The timber that you get from forest is an ecosystem service. The regulation of the global climate through carbon sequestration is an ecosystem service. The provision of habitat for endangered species is an ecosystem service. The prevention of diseases by providing habitat that is difficult for vector-borne diseases to flourish is an ecosystem service. There are many, many, many such ecosystem services. We worry about forests because if you clear forests, you lose all of these different kinds of services. Now, I'm going to use as a reference point for my discussion of ecosystem services a report that was produced 5 or 6 years ago called the Millennium Ecosystem Assessment. It was an exercise involving 1,000 scientists, not as many as you have in the Campus de Mar, but 1,000 scientists around the world to evaluate the state of the world's ecosystems. And what they concluded was that if you looked at the services that we get from the world's ecosystems, then some are doing just fine. The things that they called provisioning services, the production of foods, fuels, fibers, those are doing just fine. We've got more food now than we ever had. We've got more fuels in the way, not just thinking of timber or dung or traditional fuels, but thinking of biofuels, for example. There's more fuel produced. There are many, many more pharmaceutical products that are obtained from natural systems. So these are all doing just fine, but these others, they concluded, are largely declining. And why? It's actually very simple. And anyone in this room will understand this, that these guys, the provisioning services, are well served by markets. People can see the price that they get from the production of food. They can use that to inform their resource allocation decisions. But many of these ones here are not serviced by markets. So this is a summary of what this Millennium Ecosystem Assessment concluded. The provisioning services are listed on the right-hand panel: crops, livestock, fisheries, divided into both wild capture fisheries and aquaculture, timber and various other fibers, genetic resources, and so on. They concluded that in physical terms, this is not the value of these services, it's the physical magnitude of these services. These had all risen unambiguously. Those had risen, but there was some sufficient uncertainty that they indicated it as a plus or minus. On the other side, the regulating and cultural services, they concluded that most had declined. Now, the service that we're looking at in forests is a regulating service, and it's a regulating service governing the supply of water. So what we're interested in doing is saying, how does this service change if you change the forest cover in the Panama Canal? And if you take that in isolation, what conclusions do you reach? If you combine it with the other services with which it is jointly produced, what conclusions do you reach then? So these are the regulating services that people think occur from forests. This is the set that we're interested in. Water regulation, the timing and magnitude of runoff, flooding, aquifer recharge. Control of erosion, particularly soil retention and landslide prevention. Panama is typically a country where you get landslides. Water purification and waste treatment, slightly less important, but those are the two that we're going to focus on. There are provisioning services as well. Forests produce timber, forests produce pharmaceuticals, forests produce genetic resources, and we're going to look at those as a part of a rescue package for what seems like a really bad idea if you're interested in water regulation, and that is to reforest the Panama Canal watershed. So we're going to say, because our results tell us that it's not a great idea to reforest if you're interested in water regulation, are there other services that may make this a good idea nonetheless? That's where we're going with this. There are these cultural services as well. I'm not going to spend time talking about any of these, but I know from the fact that I supervised Julia Tuther's thesis on forests in this part of the world, that there are many forests that generate very significant cultural services. And it is true in the Panama Canal watershed that there are important cultural services in the form of biodiversity protection. I'm not going to take those into account in what follows. Deforestation occurs around the world, but according to the Millennium Assessment, it's primarily in these red areas where deforestation is occurring most rapidly. Most of the deforestation that the Panama Canal Authority is trying to reverse occurred 100 years ago. It's not new deforestation. This is what's happened for all of the different forest types. What we're talking about here are tropical dry forests. So it's this category that we're interested in respect to the Panama Canal. So what's the economic problem? It's actually a really straightforward problem. The economic problem is if you have joint production of ecosystem services, some of those are marketed, some of those are not. What are the conditions that should be satisfied for an efficient allocation of resources? How do those compare to the current allocation of resources? And can we identify means of bringing the current allocation closer to the efficient allocation? Because it's a system of joint production, we have implicitly a joint production function of this general form. We're looking at a very similar, simple system where we're going to be taking dry season water flows, a regulatory ecosystem service, along with two other ecosystem services, carbon sequestration and timber production, and we're going to evaluate the conditions in which those would efficiently be allocated across the watershed. So the problem that we take to be of interest to the Panama Canal Authority is to optimize a function of this general form where V is a measure of the net benefits that accrue to the constituents of the Panama Canal Authority, and where those depend upon a bundle of services. And if you just look at the, each of these is a partial derivative. So the partial derivative of V with respect to the inputs is a measure of the marginal value of those inputs, the marginal value of the case service. WJ is a measure of the marginal cost of the land, the jth land cover type. And as you would expect, what we're trying to do in this case is to satisfy these conditions, that the rate of transformation between D, which is the dry season water flow, and a bundle of ecosystem services that includes carbon plus the production of timber, that should be equal to the ratio of their marginal values. So we're going to take that efficiency condition and we're going to model in a spatially explicit way the allocation of resources across the watershed and see if we can identify where it makes sense to reforest depending upon the services that are being considered. So we're going to try to identify locations at a 30 square meter resolution where the cost of land cover is equal to the value of the marginal product of that land cover type with respect to dry season water flow. We're going to take dry season water flow as our reference point and then ask about the value of other ecosystem services with respect to that. So what we've done is to specify and calibrate joint production functions for that set of services and estimate the areas over which the efficiency conditions are satisfied. It's a way of answering the question, should the Panama Canal Authority reforest the watershed? As it happens, they are going to do this anyway, regardless. But we're asking the question, is this an efficient use of resources? Why they're worried? Well, I've already given you some indication of this. This figure here, I know it's not very clear, but this figure gives an indication of the water levels in the Gatun Lake over the year in each of the years that are indicated here. And if you take a look at the general pattern, it's one in which during the dry season the water level goes down and then it resurges, and in the wet season the water level is above the maximum level of the dam in Gatun Lake. This only goes up to 1996, but even so you will see that on this occasion, this would be 1973, it exceeded this level here. That level is the minimum level of water that's needed to fill the locks. So when the level of the lake goes below that, the locks cannot be filled, and the canal simply stops. This problem has been getting worse. In 1998, an El Niño event saw the same phenomenon occur, and in fact the Canal Authority imposed draft restrictions on canal users for 4.5 months in the middle of that year. So this is without post-Panamax. This is without the expansion of the canal, and their worry is what's going to happen when they expand the canal and they need to fill the locks in the middle of the year. We're going to look at the watershed functions. I've already indicated what some of these functions are. We know that the watershed functions are thought to be at risk for these various reasons here, and our problem is that we are in a system, a tropical system, where evapotranspiration can exceed the amount of the water that flows down into the soil and then into the water courses, the rivers, and so into the canal. So we're constructing a spatial model at a 30-meter resolution for the whole of the Panama Canal watershed. And we're using a very particular approach for the hydrology. It's an approach associated with these people here in et al., which uses a model that was developed first to deal with storm runoff. And we've generalized this to deal with annual precipitation. We've then used that to calculate the net runoff into the Gatun Lake over a range of environmental conditions that match the rainfall history associated with this area. And I'll give you just some of the results. You'll see them all visually in this way because it's the way that in a spatially explicit model the results are generated. So this is the predicted spatial distribution of dry season water flows. And what you'll notice is that if the area is colored red, there are no dry season water flows whatsoever. If the area is colored dark blue, there are significant dry season water flows. And the general pattern is that the dry season water flows over much of the watershed are less than 200 millimeters, so relatively low. And this is what's going to turn out to be the problem for us. So this is modeling the current set of flows. What we then do is to say, if we were to reforest the watershed in certain ways, what would it do to these results? Groundwater recharge is indicated again in this diagram. Zero recharge is all of the red areas here. And once again, recharge is fairly significant in the western region and a particular location here, dependent on soil type. But for most of the area, the groundwater recharge is relatively low. So the big problem in reforestation is evapotranspiration. Put in trees, they pump water out of the soil, and they release it to the sky. It's as simple as that. As a first approximation, what we need to do is to model that production function, which we do, and we then need to have some indication as to what the marginal value of the service is. We take, as a first approximation of this, the revenue generated by each cubic meter of water that enters into the canal in the dry season and used in a lockage. That's our first approximation of the marginal value of that. Currently, 37% of the forested area, that's the area in the west, right, the area at the top of our diagram, that area has a positive impact on dry season flows, and it generates some revenue stream to the Canal Authority. At the moment, only 4.3% of the existing grasslands would be capable of providing a benefit from reforestation if the benefit is limited to water flows in the dry season. So essentially, our first result, just looking at the marginal, using the marginal value of a cubic meter entering into each lockage, our first result is that if you were to reforest the watershed by turning all existing grassland into tree cover, that only 4.3% of that would pay for itself. This is an image of the water flow value of existing forest cover, and you'll see that this is the area that is covered by forests at the moment, that it is positive over a reasonable part of that area, but not all of it. In some instances, it's negative. Negative values in this case are shown in black because it's the most obvious color, not because it accords with our notion of being in the red or being in the black. So negative values in all of the maps I'm going to show you appear as black. And you can see that there is, just looking at existing forest cover, all of the forest area in the neighborhood of the canal generate negative values in terms of water flows, positive values in terms of the limitation of landslides and siltation, but negative in terms of water flows, and negative in much of the catchment of this Madin Lake. So if you convert existing grass cover to forests and you just look for the value of that in water flows, the picture is almost all black. It's just not a good idea. And it appears that this is not especially sensitive to the hydrological model used, that you would have to have a hydrological model that had a completely different evapotranspiration rate associated with it to get anywhere near to positive values. So there is a problem. And now what we ask is, well, okay, they're going to reforest the watershed anyway. Is this just a complete disaster? Are they going to find themselves with less water and less value from every hectare of land converted, or nearly every hectare of land converted? So we then ask the question, well, what happens if you look at the joint products, the other ecosystem services? If the Canal Authority is going to pursue a strategy of reforestation, what should it be doing? The answer is, if you're only interested in water flow, it shouldn't be doing it at all. It's inefficient. So we look at these other services here: sequestration, livestock production on the current grassland, commercial timber production, and see if that makes a difference. And it turns out that it does make a substantial difference. You may not be particularly interested in the aspects of the modeling exercise that deal with carbon sequestration or timber production, but I'll just spend 1 minute explaining these. To get at carbon sequestration, we've taken estimates that were done across the whole of the watershed for different types of forest, mature primary forest and secondary forest. We've augmented those to allow for carbon contained in roots, carbon contained in leaf litter, and carbon contained in the understory, and that's given us these values for carbon per hectare for the two kinds of forest, primary mature and secondary forest respectively. We've taken a conservative value of that, $4 a ton. As you know, the value of carbon has been declining, much the same as the value of sulfur in the American sulfur trading system, which has now gone to zero, but not for the same reason. So if we then say, given that story, if we convert the existing grassland into natural forest, what does it do? Once again, if you look at the pattern here, remember the black is the negative value, so that's the areas where those efficiency conditions are not satisfied. It turns out that the conditions are satisfied in some parts, in a very spatially disaggregated way. But there are some parts where it becomes interesting, it becomes efficient to convert if you take into account carbon values and if you convert to natural forest. So the next thing we did was to say, well, what if the timber has value? And we did, because it is a common plantation crop in the area anyway, take a particular timber stock. So this is teak, Tectonus grandis. And we used essentially the data that are available on that industry in the Panama Canal watershed at present. And then estimated the carbon stocks over a 3-rotation sample where the average rotation length is 25 years. Arbitrarily, we have taken a price from 2009 and then used that to conduct the same exercise. And if you now look at the carbon, dry season, water flow, and timber value of converting grasslands, then what you see is that all of the black disappears, that it is in fact an efficient allocation to efficient use of the grasslands to convert if they are being converted to high value teak production. And if we look across both the grassland conversion and existing forest, combine all of those values together, this is the image that we get. Across the watershed, it would be efficient to convert, providing that the original existing forest is left intact in the areas where it does generate value for water regulation, and in the other areas is converted to a high value crop. Now, teak doesn't do as well in terms of water provision, so it provides value in the form of a commercial product. So the Panama Canal Authority would have an exaggerated water supply problem at the end of this. It would be efficient, assuming that they can put in place a mechanism that will enable them to maintain the locks in production during the dry season. But that's going to become an increasingly difficult challenge to meet. So what are the implications of this? Well, scientifically, we would say one implication is that if you take a look at jointly produced ecosystem services separately, and if you focus on particular scales, you're always going to have a problem. And if you want to model the problem effectively, you need to understand the spatial distribution of the costs and benefits of those services. How would this issue be resolved in the case of Panama? Well, again, by instinct, we would say that if this is an area where there are gains to be had from a reallocation of resources, but that reallocation is not taking place because there are no markets for carbon, or there are no markets for dry water flows, or where there are markets for such things as teak production, there are capital constraints that prevent people from investing in the generation of teak plantations. How would you resolve that problem? Through intervention which changes the incentives, through the creation of either property rights, through addressing the capital constraint problem, or through what I'm going to talk about momentarily, which is payments for ecosystem services. PES schemes are just an example of the creation of markets. And these have been used in many parts of the world to deal with the supply of water. The areas on this figure here that are colored green are countries where there are PES schemes for watershed protection already being implemented. These are just creating markets for services that are important but haven't been recognized. In the United States, the Catskill watershed is our best known example. where a market was created to use the watershed to clean up water rather than to invest in a water cleanup plant in New York City. But there are many, many places around the world where this is now occurring. What you're trying to do in such cases is to take a look at the benefits that accrue remotely from an activity that would by itself generate under-provision. So let's just say we'll call the carbon sequestration problem, for instance, conservation of the carbon stocks through conservation of the forest. If there is a supply cost to that, if the local benefits associated with that activity as such, then you'll generate a level of activity that will be socially inefficient if there are a wider set of benefits to others. And what we're trying to do in the case of the canal watershed is to close the gap, to try and build the benefit that accrues not just to the producer of a product, but to the canal authority and to all those who benefit from the existence of the canal. So to conclude, it will come as no surprise to anyone that if there are externalities of this kind, and those externalities have one sign or the other, positive or negative, that the solution to a problem is going to be to internalize those externalities. You can do that with PES schemes, providing that the externalities cover the incremental cost of co-producing the non-marketed services. Close that gap. And providing that those schemes, providing that the services are generated on land that is held privately. If land is held publicly, payments for ecosystem services are not appropriate. If land is held privately, they are. But the efficiency of those schemes depends on two things. One thing is getting the story right, understanding what the real production functions look like, understanding what the marginal value of the non-marketed external service looks like, and then generating an appropriate instrument. Many existing PES schemes fail because they're just badly designed. There is scope in the case of the Panama Canal watershed for realizing the gains from carbon through the generation of markets. Realizing the gains from teak, well, maybe only if, because this is a privately produced commodity, it's one for which there are well-established markets, only if the impediments to investment in teak could be addressed separately. So back to my starting point, if we were going to begin afresh, we would say to the Canal Authority, reforestation is not a good idea. This is not going to solve your problem in the canal, and it's not going to generate an additional flow of services of a non-marketed kind that's sufficient to cover the cost of the exercise. But if we are where we are, and you are going to reforest, how would you make it pay as best as possible? And the answer is that the only way you will do it is to convert to forest that generates sufficient value that will offset the cost to you of the reduction in dry season water flows that you need to operate the canal. And that's my closing remark. So I'd like to say once again, thanks to the Campus de Mar for the opportunity to speak to you on this. I should acknowledge Silvio Simonit for his collaboration, grant authorities and the canal for providing us with the data that was necessary to do the work. So thank you very much, and I'm open to questions.